So Lecture 1, SISO Linear Systems. In engineering, we often consider the design, mathematical modeling, or analysis of machines, circuits, biological populations, etc. We call these in aggregate systems. The vast majority of systems we consider are dynamic. They change over time. We can analyze such systems by writing mathematical representations of appropriate physical laws. That's what we're going to do here. Dynamic systems, section 1.1. For instance, a simple machine might have a link pinned and actuated by a motor at one end, as shown in figure 1.1. So hopefully you can just flip your sheet over, so hopefully you have that sheet ready to go. But this is figure 1.1. We have a motor here on some mount, and we have a link that's connected to the motor, pinned at to the shaft of the motor, or coupled somehow to the shaft of the motor. So, as with most motors, we're going to have rotational motion here of the link. So theta is going to be the variable that describes that angle of rotation. So the angle theta of the link might change with time depending on the external forces acting on it, which include the motor torque. We could apply Newton's laws to describe this motion. Things that you've learned in your dynamics class, in your physics class, that type of thing. Assuming the link's weight creates a moment about the motor shaft much smaller than the torque T applied by the motor, and letting the link have mass moment of inertia I about the motor shaft, Newton's second law in its angular form yields that the torque is equal to I, the mass moment of inertia, d, so the second derivative of theta with respect to time. Okay? What type of mathematical object is this? The derivatives make it a differential equation. So we've got the derivatives of theta here, make it a differential equation with independent variable time t and dependent variable functions of time, theta, variables, theta and t. So theta and t are both functions of time, even though we haven't explicitly denoted them as functions of time here. The derivatives are all ordinary derivatives and not partial derivatives. So our derivatives are ordinary derivatives. So it is an ordinary differential equation, or ODE, instead of a partial differential equation, or PDE. Let's assume the torque T applied by the motor is known, and that the angle theta is unknown. The unknown dependent variable theta and its derivatives enter the equation linearly. So if you look here, so theta and its derivatives show up here. Notice we don't have, for instance, a cubed here, or it could enter with like a cosine term. Clearly this would not be the great way to arrange it if it had a cosine term. But it doesn't have those, right? Those are nonlinear functions. It enters linearly because it's just multiplied via a constant. So, linearly. All right. Great. So box 1.1. So these boxes are going to help us connect the dots between this primer or among this primer and its other courses in the curriculum. So at St. Martin's specifically, but I think that these are pretty universal in many cases. So, course connections, differential equations, computer applications in engineering. So that in differential equations, you spend a lot of time studying ODEs. This primer focuses on a specific subset of material from that course and presents one unified way to solve all such problems. This primer is, of course, no substitute for the entire differential equations course. In computer applications and engineering, which is our sort of intro course for people who will be ME majors, in that course you learn some fundamental numerical techniques. Sorry, I got my notes back. For solving ODEs. These techniques apply directly to the ODEs presented in this primer, which focuses on analytic instead of numerical solutions. So that course, you're doing a lot of MATLAB, you're doing a lot of programming, and it lends itself to numerical solution. So it doesn't have differential equations as a prerequisite, but you discuss them because you have had calculus at that point. So just trying to connect you with what's going on there. Dynamic systems that can be effectively described by such equations, so such equations being linear ordinary differential equations, so linear ODEs, are called linear dynamic systems. So we introduced systems and then dynamic systems, and now specifically linear dynamic systems. Note that many systems are approximately linear. Therefore, we spend a great deal of time analyzing linear dynamic systems. In fact, early courses in physics and engineering covering topics going by names such as mechanics, electronics, and dynamics, so I think we've all had courses with those sorts of either titles or topics discussed, mostly consist of learning physical laws that have precisely this form, okay, linear ODEs. We have seen that in at least one case, and in fact in many others, Newton's second law yields a linear system description. That was with the motor example. In electronics, one can effectively describe the voltage current, or VI, relationships of discrete components such as capacitors and inductors with simple differential equations. Letting a capacitor's capacitance be C and inductor's inductance be L, we have these two equations that you should have seen before. So dV dt, so the time derivative of the voltage for a capacitor is equal to 1 over C times the current through the capacitor. Okay? And for an inductor, it's similar, but sort of the dual of that. So the time derivative of the current is equal to 1 over L times V. So these are two simple linear ODEs. And in fact, when we combine these with the algebraic relationships that arise when you apply Kirchhoff's laws, right? Voltage and current laws, then you're able to develop larger but still linear ODEs in most cases. So you can come up with nonlinear ODEs even in electronics. If you have, for instance, a nonlinear resistor, or there are a lot of nonlinear components, but at the basic level you probably haven't experienced those yet. We'll discuss those to some extent in mechatronics. As we know, circuits often consist of several such components and can be described by combining these sorts of simple equations to form those that are more complex. So in Physics 1 and dynamics, you were often applying Newton's second law to derive a system of equations. These were, in fact, linear ODEs. In Physics 2, you performed circuit analyses. Whenever a capacitor or an inductor were included in the circuit, the resulting equations were ODEs. You often, you wouldn't have probably discussed it directly because you probably wouldn't have had differential equations before taking Physics 2. So typically it's just sort of discussed in passing. Maybe it's a simple equation you can integrate, that type of thing. So differential equations were there. They've been there from the beginning, but you weren't yet ready to recognize them or solve them. So, and some more course connections. So this is sort of looking forward. So we just look back in box 1.2. Looking forward in box 1.3, course connections to mechatronics, system dynamics, and control, heat transfer, vibration theory, etc. So in a great many of our mechanical engineering courses, you will encounter linear ODEs. Investing your time in this primer will pay dividends throughout. Note that more advanced solution techniques for multiple input, multiple output systems, nonlinear systems, and distributed systems described by partial differential equations are beyond the scope of this primer. So we're not going to deal with everything, but what we are dealing with is pretty ubiquitous. Where such systems arise in the ME curriculum, solution techniques will be discussed. However, throughout the curriculum, it is often assumed that you can solve linear ODEs without too much trouble. So that's the purpose of this primer, is to say, okay, when you come up to a PDE or you come up to a nonlinear problem, that's going to require further discussion in the class. But just as we expect you to be able to perform a derivative or integrate a function without having to go back and teach that in the ME curriculum, we're going to assume that you're able to do your linear ODE solutions all on your own. So, 1, 2, inputs. These system descriptions in the form of linear ODEs often include dependent variables, meaning they're dependent on time. So it's the terminology is a little bit weird here, so we'll try to go slowly. So the dependent variables that depend on time. So we've encountered those a lot in your differential equations class. So these system descriptions in the form of linear ODEs often include dependent variables that can be considered independent of the system's dynamics. Okay, so they're dependent on time, so they change with time, but we're going to say they're independent of what happens in the system. Okay, they are therefore prescribed externally and, quote, input to the system, thereby getting their name inputs. Okay, so this is sort of the definition here of an input. What is and what is not an input depend on the system definition. So it depends on what we define the system to be, right? For instance, in our motor link example above, we made the nebulous statement that the motor torque T was known and the angle theta was unknown. Stated a bit more precisely, T was taken to be an input, whereas theta was not. This means the motor itself was not part of the system described by the ODE. However, we could have included it in the system. This would mean that T would then become internal to the system, which would require the application of additional physical laws to describe its electronic circuitry. The choice between these two options, and among others, depends on our design and analytical needs. So sometimes you might want the motor to be part of your system, other times you might not. So I think that we all recognize that we can't write down physical laws for and equations for the entirety of the universe and hope to get anything useful out of that. So we have to shrink it down to something that's more contained, and that's what's inside the system. And what comes in from the outside is going to be an input. A great number of systems of engineering interest have a single input, almost surprisingly, but it is true. In our motor link example, our single input has the torque T. In many electronic systems, a single voltage source supplies external power, and so is often taken to be the system's single input. Even systems of great complexity can often be described as single input systems. When a system has a single input, we will often use U to denote this variable. Okay. Section 1.3, outputs. When designing and analyzing a system, certain dependent variables will be of particular interest. We call such variables outputs. So we've got inputs and we have outputs. Often, only a single variable is of interest. In such cases, we say we have a single output system, and we often denote the output with the symbol y. So input u, output y. For instance, perhaps in our motor link example, we are interested in the angle theta, which we would then call an output. So if we're interested in it, that would make it an output. It turns out we were ignoring another class of variable called state variables. We'll learn about them in mechatronics. For now, let's assume that we're interested in every dependent variable other than inputs in our system. Okay, so some of the dependent variables are inputs, like the torque would be if we considered the system to just be the link, and anything coming in from the outside would be an input, right? We're going to say everything else, all of the other dependent variables are going to be outputs. An objection might be raised here. How can it be that a single output can describe the output of many systems if we're also going to take every dependent variable as an output? Like, aren't there going to be more things showing up, like theta 1, theta 2, the current voltage, which I think I just say here? Won't more variables be required to describe the dynamics? For instance, if in the motor link example, we take the system to include the motor, if we do include the motor, we'll probably need the voltage and current therein to describe it. So the motor's got the electrical side too. So if we're going to describe the system dynamics, we're going to end up with more variables than just one output. And this is a pretty simple system, so how can I claim that this is going to describe quite a few systems? Because with theta, so say voltage, current, and angle of the link, 3 outputs. That's 3 outputs, and I'm saying the single output is something that happens a lot. Doesn't seem like it could happen. It turns out we can sort of sidestep or assuage this by algebraic relationships among the variables. For instance, the current through the motor windings, right, so in our example, is proportional to the torque. So that sort of direct relationship there allows us to rewrite the current in terms of the torque. Okay. Through such relationships, we can have our cake, our single output, which is what we want, and eat most of it, which is eliminate extra dependent variables too. So we don't want to have multiple of these outputs for this specific case. We're looking only at single input, single output systems. So we would like to eliminate other outputs, and that's one way to do it. Don't worry, it's not like I'm assuming you know how to rewrite this. I'm just telling you that you can do it. The catch is that the order, which is the highest derivative of the differential equation, so the highest derivative in the differential equation we call the order of the differential equation. So the highest derivative describing a system typically increases through this process of variable elimination. So maybe you have V and I and theta and the torque, and then you say, okay, I'm going to whittle it down to just one output. So instead of 4, maybe we go down to 1. With just one, what you're going to have done, though, is actually increase the order of the differential equation. So maybe you had a nice simple first order differential equation describing part of the system and another first order describing another part of the system. When you combine them together, what happens is the order grows. So there's actually, you can stop anywhere in between there. You can go to a bunch of first order equations or to one nth order equation. So we'll learn about this. So in mechatronics and system dynamics, we'll learn that we can express a system's dynamics as n coupled first order equations or as a single nth order equation. In system dynamics and control, we'll learn to solve the coupled equations. So the coupled version, we'll learn about how to do it in mechatronics. We'll learn how to solve that. We'll do it numerically in mechatronics, but then in system dynamics and control, the course that follows on afterwards, we'll learn to solve that analytically as well. Okay. In this primer, though, we're going to learn to solve just the single nth order equation, so the single input, single output system. And that's actually where we finally arrived now. So the result of all this is that we frequently encounter single input, single output, or SISO linear systems. The input-output dynamics of all these systems can be described by the linear ODE with constant coefficients. So this is introducing equation 1,1 here. So it has constant coefficients, A and B, they're real numbers. So AI, B, J, we've got A's here and B's, but there are a lot of them, right? They're indexed by I and J. And these A and B's that show up in this equation include system parameters such as the mass, spring constants, capacitances, resistances, all of these sorts of physical parameters or parameters we're using, lumped parameters, we'll talk more about that in mechatronics. Those will show up in these coefficients, in the A's and the B's. Okay. System order is n, so an nth order differential equation, and m less than n, so n and m here are the derivative orders, right? So it's saying that n has to be greater than or equal to m. And what do we have here then? On the left-hand side, we have a summation of derivative terms, so nth order derivative of the output y with respect to time, and a coefficient, and then the n minus 1th derivative of y with respect to t, etc. So the derivatives of y are on the left-hand side of this equation. It's on top here, but the left-hand side is this top line. And so derivatives of y scaled by parameters, system parameters, and summed up. Okay. On the right-hand side, we have derivatives of u, derivatives of the input with respect to time, multiplied by parameters, constants, and summed up. Okay, so the left-hand side has got the output, the right-hand side has the input. The rest of this primer will take as its primary goal the description of a solution technique for equation 1,1. Solutions, what we'll call solutions, will be functions, whoa, that was loud, be functions y that satisfy equation 1,1 in terms of parameters a, b, and input u only. So solutions for y in terms of a and b and u. So we got to solve the differential equation. The solution is going to be functions that satisfy this equation. Now, our right-hand side, so this whole thing, it has these derivatives of the input u. And I want to mention that we're not going to really talk a lot about what happens when you have derivatives of your input in this primer. We'll talk about it more in the courses that follow, when that arises and what its significance is. But something that we are going to do to sort of simplify what we're doing here, and in fact this is a very useful technique, is we're going to give a name to everything on the right hand side. we're going to say that all of this is some function of time f of t, and we're going to call it the forcing function. So the forcing function f of t is equal to all this. So we're going to switch back and forth from talking about inputs and forcing functions, and they're distinct things, right? So u is a part of f, and if m is just 1 here, well actually if m is 0, we end up with just b0 times u, all these other terms go away. And if b0 is just 1, then f is equal to u. So the forcing function is equal to the input. But that's actually not generally true. So the forcing function is this whole object. The input is u. Okay? So that's a little bit of terminology. We're going to use forcing function here a lot more than input in these later lectures. Suffice it to say, though, that if you find the solution with f of t being equal to something that is an input to your system, you can use, there are two really key rules. One's called the principle of superposition, which is really key, and we're gonna mention it in passing in this primer, but we'll use it more later. And then the other is the differentiation rule. So if you use those two rules, you can construct solutions for systems with very complicated forcing functions that look like really big messes with lots of derivatives in them, just by essentially dividing and conquering. So we're not going to cover that, but I'm just going to mention it now. So looking forward to the next year, we'll be discussing systems that you can do this with, and we'll talk more about how to do that actually in the mechatronics and system dynamics classes. So it's a little preview, a little bit about terminology there. We've defined SISO systems. We've defined the equation that we are going to solve. We're going to be referring back to equation 1-1 like the whole rest of this primer. So this is the equation we're going to be solving. We're doing nth order. We're not going to do first order, second order, etc. We're going to do nth order. Not to say it's not important to go through first and second order. We will talk about those actually explicitly in mechatronics. But we're not going to dwell on that here. We're going to do it for the nth order system. Same solution technique is going to apply, and we'll discuss what to do when we come up with different root situations. So we'll talk about that next lecture. All right. That's enough for now.